So I'm Pedro Mendes. I'm at the University of Connecticut School of Medicine, also known as UConn Health. Although part of the work I'm going to talk about, or most of the work I'm going to talk about, was actually carried out at the University of Manchester in the UK when I was there. So this is about COPASI, which is a software for simulation of biochemical networks. It's a simulator, and how we used Condor to turn it into high throughput mode. So COPASI is actually mostly used as a standalone application. It's really written directed at biologists and chemists, basically trying to abstract as much as possible the mathematics and computing behind it. So it really is directed at people who should not need to be specialists in order to run simulations. Obviously, being specialists will help them as well, but not necessarily. So because of that, it's mostly run as a standalone application with a GUI front end. And it's portable, runs on various operating systems, etc. It's by now is very well established as a large user base. The map below shows you the various laboratories that have published papers with COPASI. We'd like to pinpoint them on the map. By now, the map basically just shows where money is located in the world, because that's where research happens anyway. And also another metric that we track, because by the way, we don't track the usage of the software since it's not server-based. We do track downloads, but that is not too informative. People can download things without using it. So we really track is the number of papers that publish research that was carried out with COPASI, and that's now floating around about 100 per year. I mean, in 2019 went up quite a bit, but then 2020 seems to have been a bad year. I think this year we'll go back again a little bit further up. So essentially, for most of the research published with COPASI, it is used as a standalone application, and everything runs on a single laptop or desktop. And many of the applications, things are fast enough that that's a perfectly good mode of operation. It does have a number of simulation types and analyses. I'm just listing here. I'm not going to go through any of these in detail, but it's useful to talk about some of them. Most of the units of computation are either solving differential equations, either ODEs or stochastic differential equations, or running so-called stochastic simulation algorithm, which is the Gillespie algorithm. Some of you may know it's a continuous time discrete event type simulation. Discrete events can also be added onto the ODEs or SDEs as well. We do calculate a number of other analyses like steady state analysis, stability, parameter scans, or people also call it parameter sweeps. As you will see, that will play a big role here. Sensitivity analysis and various other things, Lyapunov exponents, cross sections, etc. All sorts of nonlinear dynamics. And some of these things are, oh, and I forgot to mention, one of the main uses is parameter estimation. A lot of users use our software really just to estimate kinetic parameters, and that's done through least squares using a big menu of possible optimization algorithms that we have included, of various types, from gradient descent type algorithms to simulated annealing, genetic algorithms, and particle swarms, things of that kind. So when I was at the University of Manchester in the School of Engineering, or Faculty of Engineering as it's called, Engineering and Physical Sciences, we had set up a Condor pool back in around 2009, and this was led by Ian Cotton, who was also in my institute, where we actually had pioneered this with a very smaller pool, just using workstations. One of the things that Ian was really good at was he was good at convincing the faculty that all of the computer terminals that we were using, that students were using, that overnight they are basically idle, and we could turn them all into a Condor pool. So he set up a system where these machines would, during the day, be being used by students. If they're idle after a certain amount of time, they actually reboot themselves and add themselves to Condor. But then the students can interrupt that at any moment. But overnight, they are all available. And that's about 3,000 CPU cores at the stage when I left. That was the number. It's possibly more now. And then during the day, we had a few machines dedicated to be there on the pool. So they would be, processing was slower during the day, about 100 machines. Some of them were several large multi-core machines, but not all. So essentially, we had a nice system. And with COPASI, we were really keen to try and use this as much as possible. So we actually were some of the very first adopters of this pool. At some point, the people in astronomy and so on discovered it, and they were basically flooding all the cores. So I decided to start using COPASI with Condor. And what can you do? Well, you can look at those operations that essentially run many times the same units that are independent, such as parameter sweeps that have to run many simulations with different parameterizations, or repeating stochastic simulations, which is basically each one is the same initial conditions, but because they're stochastic, you want to repeat them to draw a distribution, time-dependent distribution, etc., things like that. So how do you do that? Well, obviously you have to do the following. The first step is to create a model in COPASI and a GUI, and you save it. You actually have to create a report file, because when you run it from the command line, there's no interaction. The software just writes all results to a report file. I forgot to mention that there is a command line version that just runs the simulations essentially that the files indicate. There's no interaction other than that. So in the GUI, you have to set up everything such that you will be running the operation in a remote mode. And then you have to save this, and then you have to prepare a Condor, HTCondor job specification file, which there's a little example down there. We actually do have COPASI for various architectures. So our Condor pool was multi-architecture. So we also had requirements in there, what types of the executables we could use, and what machines could be available. We could try to use all of them, in fact. Then we have to prepare some output directory, submit to HTCondor. Then results come back, and then we have to edit the results such that they match the required order. So for example, if I was originally going to do a parameter sweep, changing 3 parameters and 10 values each of them, and it's hierarchical, then you basically have you expect a certain order in the output. And downstream processing may depend on that order. So what we do when sending the software to Condor is that it was important to also structure the output such that it comes in the right order, the expected order. And then sometimes you want to create some summary plots, etc. So this was all done manually for a while. Then comes Ed Kent. Ed was a PhD student that came to my group, and he was very, very good computer scientist. In fact, his background was in computer science, and he basically said, well, I can do something and automate all of this. So he created a package which we called Condor-COPASI. By the way, this started at the time when I think was still called Condor rather than HTCondor. And what that software does, it's basically a web-based package that essentially runs on a dedicated Condor pool. Well, it has to have access to a submit node. It self-registers users. The users basically just add a little bit of information so they can be contacted by email, and that we can decide who can access this or not. And then the software, the backend, is written in Python, and basically what it does is that it takes an input file, a COPASI input file. It actually does all of that manual processing of setting the right reports and splitting that file into many files. If we're going to parallelize, of course, you want to divide the jobs into various bits, and then also does all of the reassembling of the output, and it creates also some other plots. Now that software is open, it's on GitHub. Other people have installed it. In fact, we knew about a number of other groups that have used it, including some in industry, but also various other places at academia. We did publish a paper, so this is all published back in 2012. And just to give you a little bit, I mean, this is probably not so great for this audience. This is what I show normally to the people who don't know about high throughput computing, but that's basically how this goes. The user just sends one file to the server. Everything else happens behind their back, and eventually they get the result files back from the server. I think I've gone through most of this actually. Oh, there's one part that I didn't mention, which is what at some point Ed figured out that there would be good to try and balance the load on the various cores. So he did a bit. He added a little bit of load balancing or trying to measure the speed of each subtask so that you optimize that. And I'll talk about that in a slide or two in more detail. So other than that, basically at the end, the results, the results can be several files, so they all get zipped, and the user gets sent an email that says, so you can go to this link and download your results. They can also go to log into the software and check what's the process, if it's being processed or if it's waiting, etc. Now, the number of tasks that we've added, so these are specific tasks that the software carries out. It's not all of the functionality of COPASI. It's only the things that we found easy to frame into a high throughput mode. And that one, as I mentioned, is stochastic simulation repeats. That's very simple. It's basically running the same thing over and over. And then at the end, you do some processing because you want to calculate distributions. So for every time point, you can draw the whole distribution there and calculate standard deviations, etc. Parameter scans, parameter sweeps, these are also very obvious. They include also repeats. The COPASI has a very nice way of allowing you to specify a combination of changing things regularly in a regular grid, which is what we call a parameter sweep. Sampling values from within a distribution. So a parameter can take random values according to some distribution, or repeating things. So you can basically nest each of these inside each other. So it can be complicated processing. There's an approach which is for optimization of sensitivity coefficients. This is an approach of trying to find out about the global sensitivity of a model. Global sensitivity analysis is an approach we developed earlier on, where you ask for the maximum and minimum possible sensitivity for each parameter in the model, given that all parameters can change within a large interval. So that's basically using optimization algorithms, and it's done by, for each parameter in your model, you have to run a maximization and a minimization minimum. So if you have a model with 20 parameters, you have to run 40 optimizations essentially, which is each one of them, of course, are independent. You can do parameter estimation, and because we have many different algorithms and some of them are stochastic, you may want to repeat them. So you don't want to run a genetic algorithm once, you may want to run it with random starts at maybe 10 or 50 times. So that is also allowed very easily. Same thing with optimizations, because software can also allow you to optimize any arbitrary function, not just doing parameter estimation. And then finally, you can do parameter estimation with all the algorithms. So the user specifies a problem, and rather than picking one algorithm to solve the problem, you can say, well, try it with all the algorithms. So each process then runs a different minimization using a different algorithm. That can sometimes be useful when you don't know which one is going to work best. So the front end looks a bit like this. So it's essentially a very simple page where the user has to upload the file and give it a job name, and basically say, depending on the functions, for example, in the parameter estimation repeat, you have to say how many repeats you want. There may be some extra files needed, etc. So it's very simple page that they have to fill in. And then here are some of the types of results. So I'm showing here in this fancy plot, this is a stochastic simulation, which was repeated, I think, in this case, 1 million times. And the distribution you have in shaded is the one standard deviation of that distribution, the time-dependent distribution. So you can see what areas, what parts of time are more variable. Underneath is a global sensitivity optimization, where basically for each parameter here, you show the minimum and the maximum sensitivity that the model has towards that parameter, or that the output variable has towards that parameter. And so it is a nice way of allowing users who don't need to know this computing approach, and of course would be completely intimidated by Condor, to have them enable them to use high throughput computing. Now, just to mention the load balancing, which was basically the only real bit of research that Ed had to do in this, was to ask the question, so if I have a parameter sweep with 1 million steps, how do I do this? Do I submit 1 million jobs, each one doing only one step? Do I submit 100 jobs, each one doing 100,000 steps of this. 100 jobs, each one doing 10,000 steps of this. How do you partition it, and would it be optimal? Of course, if you have 3,000 cores, you could think that you'd just chunk it in 3,000. If you could own the pool yourself for a while, that could be one approach. And of course, it may be not optimal, actually, depending on the jobs you're running. So what he studied was how this is a plot that shows you the time that the job takes to run. Actually, the time that a single job takes to run versus the wall clock time that you will get. And this is the same task. So in this case, that means this job takes a long time to run, about 1,000 minutes. That means that it's running many, it's basically running many units of computing there. And of course, if you, and because it runs so long, you're only going to need a few CPUs, so you don't really get a lot of optimization because you're running basically everything in 1 or 2 cores. So if you start decreasing that time, basically meaning increasing the number of jobs, you more or less get a linear approximation, increase, as you would expect. However, at some point you start getting overhead. Over here, you start getting overhead. Basically, these jobs are now too short to be to accelerate anything. So you're going to spend too much time submitting, transferring files, reassembling data, etc. So we found out that the ideal time was around jobs that take around 15 minutes. If they're shorter than that, we actually don't gain too much. At some point, you actually lose. You end up spending more time in the pool than you would be just running it on a much, well, not on one if you have 1,000,000 jobs, but certainly on a lot less than the number of cores you have. So we found out that the optimal is around 15 to 20 minutes. Of course, this was specific to the Condor pool, and this picture will change, or at least the scale will change depending on your pool and what is the typical usage it has. So this is a real world test. This was run in a production system that is having other users running as well, competing jobs, etc. So the software has a parameter that the administrator who installs it can change, which is what's the ideal size of a job, what's the ideal time for a job. And then what the software does is that when you submit a job that has many units, it runs one of the units to try and assess how long it takes. If it takes more than this optimal time, it just submits one job per unit of computation. If it's less than that, it submits as many in one chunk that more or less ends up taking that amount of time. The user also can click a button and say, I don't bother wasting time doing this, because if you know you're going to run a simulation that takes an hour, you don't want it to spend an hour just testing how fast it goes. You're actually better off using that hour already to run a few of them. Okay, so now moving to the present. I mean, actually, Ed started this. He decided to then use Bosco and not just be dependent on Condor, but allowing this process to run on a number of other systems, just Slurms or SunGrid engines, etc. But that eventually got stale, the code, the Python backend, many packages updated. Eventually, Ed got a job and left my group. And so this basically became a little bit of software rot. And now Hassan Beg in my group is joined last year, and we started reviving this process and basically converting to new versions of Django and Python 3. And in the meantime, also new versions of Bosco and Condor. So we're still in the process of fixing this, but it's essentially a similar thing, but now it allows you to run on different other queue managers, and including also AWS, where you just start up a Condor cluster on AWS, run things there, and then you shut it down and come back. And we are also going to add a few more use cases, a few more tasks. This one here, there's not much to spend with the equations here. This was from another presentation, but it's called profile likelihood. So you basically draw, when you do a parameter estimation, you estimate values for, let's say, 20 parameters. You want to know how identifiable each one of them is. That is, is that value really well determined, or could it be very different? And one good way of assessing that is creating these likelihood profiles, one-dimensional likelihood profiles. And what you do is you fix that single parameter that you're studying, and you set it at different values. So you essentially do a parameter sweep for that parameter. And for each value that it takes, you run a whole parameter estimation of the remaining n-1 parameters. And you note what is the sum of squares or the likelihood or whatever metric you're using. And essentially you trace how that changes as the parameter is changing value from the optimal one. And you do that for all the parameters. So if you can imagine, this is very time consuming. This is an example of what you get in at the end. So here with a star, you have marked the optimal parameter value. And now in this case, we run 1, 2, 3, 4, 5, 6, basically 12 simulations, essentially 12 values of that parameter. So
sorry, Pedro, you have 2 minutes left.
Yeah, this is my last slide, so it's working out. Thanks. So we change the parameter, we make it a different value and run the parameter estimation again, and that's the best sum of squares you get now. And then you change it again and you get that value. And in this case, this parameter has a nice valley around the value we determined. This actually means that it's very well determined. This parameter here, it's not, it's very shallow around the optimal value. In fact, if you change that optimal value a few orders of magnitude, you don't get much change unless you get to some point. So this one is not really very well determined. On one end, at that end, it's so the parameter cannot be larger than this region here. But so you gain a lot of information. But as you can imagine, there's a large number of simulations. So if you're doing k steps and you have n parameters, it's k times n optimizations, which again is k times n independent jobs that can be run easily. So the idea is to have this as another task. The user just has to submit the parameter estimation file, and then the software would automatically run all the processes and return these images already. So coming to my end, I'd like to acknowledge a number of people, definitely at Kent, who wrote the original software at Manchester, and Hassan Baig now in my group here at UConn Health. A couple of collaborators that are now at the University of Virginia, Stephen Hoops and Brian Clun, also helped a little bit with this new version, Cloud-COPASI. Of course, the COPASI team, which is multi-institution international collaboration between my group, Stephen Hoops' group in Virginia, and the group of Ursula Kummer in Heidelberg. And funding, Ed had a grant from the BBSRC and EPSRC in the UK. COPASI has been funded by an R1 for a number of years here in the US, and now it's funded by an R24 mechanism from NIH. It's a resource grant, basically funds COPASI and a sister application simulation tool called VCell from our colleagues here at UConn Health as well. And that's it. Thank you very much.